Have you ever just stopped and wondered, why is it so ridiculously hard to get different software programs to talk to each other? I mean, it's one of the oldest, most frustrating problems in all of computer science. Well, there's a new technology emerging that might, just might, finally solve it for good, acting as a true universal translator for all code. Okay, let's get into it.
It really feels like it should be simple, doesn't it? But it turns out, the very thing that makes modern software so incredibly powerful is also what builds these massive walls between programs. To really get why the solution is so exciting, we first have to understand just how deep the problem really goes. Just think about how we build software today. We use C++ for high-speed game engines, Rust for super safe systems code, Python for data science, and of course JavaScript for the web. And don't get me wrong, this specialization is awesome. But what it creates is a digital Tower of Babel. Each language has its own memory model, its own idea of what a string is, its own way of seeing the world. And getting them to communicate, it's a total nightmare.
So for decades, developers have had to rely on this kind of dark magic to bridge these different worlds. It's a technology that seems to work on the surface, but underneath, it hides some really deep, really dangerous flaws. It's called the Foreign Function Interface, or FFI.
FFI is basically the old school way to make, say, a Python script call a function written in a super fast C library. I mean, it's the glue that holds so much of our existing software together. The problem is, this glue, it's brittle, it's toxic, and it is an absolute nightmare to work with.
Okay, here's a way to think about it. Imagine FFI is this really clumsy translator who only understands a super primitive, context-free dialect. To communicate, a sophisticated language like Rust has to take its beautiful, rich concepts, like a string that knows its own length, and smash them down into these crude parcels, like raw memory pointers. Then, the language on the other side has to manually and very carefully try to put them back together, just hoping it gets it right. And when it goes wrong, it goes spectacularly wrong. This whole manual process is a breeding ground for bugs, memory corruption, and some of the nastiest security vulnerabilities you could imagine. It basically punches a giant hole through all the safety nets that modern languages give us. It creates a mountain of technical debt on a foundation of sand. Let's be clear, this old way is fundamentally broken. And when you put the old way and the new way side by side, wow, the difference is just night and day. Where FFI was unsafe by its very nature, the component model is secure by default. It swaps out primitive C types for rich, complex ones. It trades messy, implicit contracts for explicit, verified ones. This isn't just a little improvement, it's a completely different way of thinking. So what is this huge paradigm shift? It's called the WebAssembly Component Model. It's a brand new specification, layered right on top of WebAssembly, that completely redefines how software modules are built, how they're described, and most importantly, how they're put together. See, core WebAssembly, or Wasm for short, was an amazing first step. It gave us this universal compile target, a way for Rust and C++ to run in the same virtual machine. But by itself, it was kind of like having a box full of these incredibly powerful custom-machined engine parts with no standard bolts or screws to connect them. They still couldn't easily pass complex data back and forth. This is where the component model comes in. It's the missing piece. It's the universal studs and tubes for all those custom parts. It's the Lego connector. It defines a standard way for components to say, here's what I need, and here's what I provide, so that a component from Rust land can perfectly and, crucially, securely snap right onto one from Python land. And what this does is it unlocks two absolutely game-changing properties. First, you get true interoperability with rich data types. No more manual, error-prone translation. It just works. Second, you get effortless composability. You can literally wire components together, linking them into new, larger components, just like snapping Lego bricks together to build a spaceship. All right, so how does this new magic actually work? How does it pull this off? Well, it all comes down to a few core technologies that work together to create this incredibly robust universal translation system that, for the developer, just operates completely behind the scenes. Well, first up is something called the Canonical ABI. This is the absolute foundation. You can think of it like a Rosetta Stone for data. It defines one single, unambiguous memory layout for every high-level data type.
So a string means the exact same thing to every single component, which just eliminates the entire class of translation errors that plagued FFI. Okay, next up, we have WIT, which stands for WebAssembly Interface Types. Now, if the ABI is the universal grammar, then WIT is the spellbook. It's a language you use to write the contract, to formally describe a component's boundaries. A Rust compiler and a Python compiler can both read the exact same WIT file and then automatically generate all the code needed to talk to each other, perfectly.
And this idea gets even more powerful with something called a world. A world is basically a blueprint that defines a component's entire universe. Every single thing it needs to import from the outside world and everything it exports back out. This creates a formal, verifiable contract not just between two components, but between a component and its host environment.
And here's the kicker, and this is huge. All of this is built on WebAssembly's secure sandbox. A Wasm component can't do anything by default. No file access, no networking, nothing. It can only perform actions that it has been explicitly granted a capability for in its interface. So, a dependency that doesn't ask for network access is cryptographically guaranteed to be unable to make a network call. It is security by design from the ground up.
Okay, the tech is clearly brilliant, but let's zoom out. What does this actually mean for the real world? Why should you care? We are talking about the dawn of an entirely new era in software development, the component age. Well, for starters, let's talk about speed, especially in the cloud. You know that dreaded cold start problem in serverless computing? That's because traditional containers can take seconds to boot up. Wasm components, on the other hand, we're talking milliseconds. That's a transformative, orders of magnitude difference that allows for way greater density and efficiency. And hey, don't just take my word for it. This is not some academic theory. The industry's heaviest hitters are all in. You've got the Bytecode Alliance with members like Google, Microsoft, and Intel driving the standards, and then you have companies like Adobe, Figma, and Shopify already using this in production today to power their apps, from Photoshop in the browser to critical back-end business logic. But honestly, the ultimate vision here is even bigger. It's just so cool. Imagine a universal plugin architecture. Instead of every single app, from your text editor to your web server, having its own proprietary plugin system, a developer could write a plugin once in Rust, Python, Go, whatever they want, and that one single secure component would just run in any host that supports the standard. VS Code, Nginx, Photoshop, all speaking the same language. So what we're looking at is more than just a slicker way to connect code. It's a fundamental shift in how we build, distribute, and compose software. It's a technology that finally promises to tear down that digital Tower of Babel. Which leaves us with one final, really exciting question to think about. What gets built when all software speaks the same language?